looks like the apartment. Oh, really? Oh, yeah, it does. Oh, yeah.
Okay, let's go ahead and get started. As you can see, we've got a lot of demo equipment up here. I was busy yesterday fabricating some things, and I think it's going to be fun. I think it's going to be fun for me. We're doing really good on that exam. Okay, the people that have taken the exam already have aced it. Last time I looked, there were 19 perfect scores. So it's doable, very doable. Would someone be willing to give us an opening prayer this morning? Pray for our demos. Okay, I'll do it. Our dear kind Heavenly Father, we bow our heads in gratitude for the blessings which we have received at thy hand, that we are able to meet here together and to enjoy one another's company as friends and fellow students, that we are able to study at this wonderful university. We are grateful for thy Spirit, which helps us to understand and to have insight into things that we haven't learned yet. We ask, Father, that thy blessing might be upon these wonderful young people as they face so many crossroads in their lives, as they make so many decisions that are going to have lasting impact. Please bless them that they might know of a surety that they're going in the right direction. We ask now a blessing upon myself that I might be able to clearly explain the concepts that we are covering this day. And this we pray in the name of Jesus Christ. Amen. Okay. We're going a completely different direction starting today, and that is we're going to talk about magnetism. And magnetism we're going to find is just way fun, very fun. What I'm showing here is what's called a baseball coil, and this thing is 2 stories tall, and there were 2 of them created to be at the ends of what was a magnetic mirror machine that was supposed to try to create the same conditions that exist on the sun, so that we could create nuclear fusion. This was an enormous machine in a building the size of a essentially a football field. Now, when I went to interview for the job that I got at Lawrence Livermore National Laboratories, when I got there, there were all of these limos and there were dignitaries, and there's a big to-do. And all of the dignitaries and all of the visiting scientists looked very, very depressed. And that's because they were there for the dedication of this magnetic mirror machine. It was finished, it was ready to be turned on, and they were there to cut the ribbon. And everyone was upset because just the weekend before, the Reagan administration had decided that they were going to cancel the project. And so they were there not only for the groundbreaking ribbon cutting, but also for the mothballing of this machine that never got turned on. Your tax dollars at work. Anyway, Ronald Reagan decided that we would make a space shield that would protect us from everything. And we had to immediately start working on that instead. That didn't work. So anyway, that's an example of a very huge magnet, a very, very huge magnet. How many of you seen the Northern Lights? Okay. Yeah, that's a magnetic effect that we're going to understand before too long. They come in all sorts of varieties there. And essentially, these are charged particles streaming from the sun coming to the earth And when they get to the Earth, they encounter the Van Allen belts of magnetic field that causes them to stream along the field lines and come down at the North Pole and the South Pole. And as they come down through the atmosphere, they excite the molecules of the atmosphere, which then re-radiate that beautiful light. And you get these patterns. Now, in Montana, I had a friend who ran a satellite. Okay, a lot of people don't have their own satellite. He did, and so he would send out a little warning when there was a disturbance on the sun, something like that, a solar prominence that would spew these charged particles towards the Earth. And then he could give us some warning as to when one of these beautiful aurora borealises was going to appear in the sky. Now, here's a picture. This is taken in X-ray wavelength, but it's a picture of one of these prominences. And for comparison, that's the size of the Earth. And so this is big, okay? Mucho bigo. That's all the Spanish I know. I went to Germany on my mission. Okay. Again, there's another prominence that's about to spew charged particles our way, and there's the size of the Earth up there. Okay. What do we know about magnets? Well, when we started talking about electric fields and charge, we found that a magnet is not a charged rod. It's electrically neutral as far as the electric force is concerned. We know from experience that there are two poles on a magnet, a north and a south, or as we've got them here, red and a yellow. And we also know, okay, that's not gonna work. Putting that next to that great big horseshoe magnet is just gonna change everything. We know that two north poles are gonna repel each other. And we also know that two south poles are gonna repel each other. And we know that a north pole will attract a south pole, okay? And you've known that for a long time, I hope. Okay, like poles repel and unlike poles attract. And that's why we were tempted to think of this as charge, because we knew that like charges repel, then opposite charges attract. But this is a different phenomena that's going on here. The question is, can we ever find an isolated pole, a north pole all by itself? Okay. Now, I will tell you that many, many years ago, one professor at Stanford was able to find a single, we call it a monopole. No one has ever been able to duplicate that finding, and now other scientists just make fun of him. Okay, we don't believe that it's possible to isolate a single North Pole or a single South Pole. Whoops. Yeah. If I take this horseshoe magnet here and if I use a compass, the south, you see that the north, the red end of the compass is going to line up with the magnetic field. And you see that I got the south pole of that little compass needle attracted to the north pole of that horseshoe magnet. And if I bring it over here, it's the north pole of the little compass needle that's pointing towards the south pole. If I use my professor strength to rip that, oh, that seemed easy. If I were to rip that apart, what I would find is that I've still got a North Pole there, but I have a South Pole there. And indeed, if I take this other piece, I still have a South Pole there, but I have a North Pole there. And no matter how many pieces I tear this in, I could tear this into teeny tiny pieces, and we would always find both a North Pole and a South Pole. Now I'm gonna get that out of the way so it doesn't interfere with some of our other demos. That's the trouble with teaching about magnetism. Everyone's playing. Okay, they all play. So let's get back to what we know. So they always come in matched sets, one north with one south. And the way we think of this is that for ferromagnetic materials like iron and cobalt and nickel, there's a magnetic dipole. You remember what a dipole was when we were talking about electric fields and forces? A dipole was a positive charge and a negative charge that were the same size, that were together, okay? Now, a magnetic dipole would be a magnetic north and a magnetic south. It's a little compass needle or a little bar magnet. Well, we think that, well, we're quite certain that each atom of iron has its own dipole, and essentially a little north and a south. And then in unmagnetized iron, just a regular hunk of iron, those dipoles would just be randomly oriented. They'd just all be pointing different directions. And if we magnetize that, we do that by lining them all up, and I'll talk about how we line them all up in a later lecture. But once we do, we get a very strong north at one end and a very strong south at the other end. And then if we break it in two, we still have a north at this end because of these little dipoles that are aligned at the molecular level. And no matter how finely I break this up, even down to a single atom, I still have a north and a south. Now, the magnetic field is, in principle, very similar to the electric field, okay? It's a way of explaining an action at a distance. We know that this magnet here was affecting that magnet over there without touching it. And so we say that the first magnet sets up a field, and then that field pushes on the second magnet. The same game we played with the electric field and the electric force. Now, the operational definition we give to the magnetic field is a vector whose direction is indicated by a compass. In other words, if I take a compass, which is really just a small bar magnet, that compass will line up with the field that it finds itself in. The field is in the direction of the north-seeking pole of the compass. Now, my compass has a red part of the arrow that points towards Canada, which is north of us, and a white part of that arrow that points towards Mexico, south of us, okay? And so the north-seeking pole of this compass is defining the direction of the magnetic field in the room, okay? And that magnetic field in the room is going to change as I move around the room because of all of these strong magnets that I have in here. But if I weren't around all of these magnets, I'd be dealing with the magnetic field of the Earth. And the magnetic field of the Earth points north, okay? And down, okay? It points north towards Canada
and down 70 degrees here in Provo. So it would be pointing about that direction there. Now, we use the label B for magnetic fields, and again, this is historical. We named it B to honor Biot Savart, who taught us a lot about magnetic fields. We often use iron filings to act like little compasses so that we can visualize the magnetic field due to some compass. Now here, I have a representation of what those, so that's a picture of it. You see those iron filings are kind of making these patterns that come out of a north and go into the south. What we have here is the same representation. We have a strong magnet, strong north pole, strong south pole, and these little things are free to rotate, but they have lined up to essentially help us visualize the magnetic field of that strong bar magnet. Now, let me see if we are on the bus. If I have this bar magnet that's free to rotate about that red dot, and it finds itself in this external magnetic field, we call it a B field, what direction will that bar magnet rotate, clockwise or counterclockwise? This is not a clicker question. Just tell your neighbor which it'll be. Okay. I hope everyone said that it would rotate clockwise 90 degrees, okay? Clockwise 90 degrees, so that the north end, the north seeking pole of that bar magnet would line up with the external field. Now, you can think of this as a compass needle where the arrowhead is on the north seeking side, what we call the north pole of that bar magnet. Now, if I wanted to explore the magnetic field due to a bar magnet, what it looked like, I would just take a compass and set it next to the bar magnet. We did that just a moment ago. And you see that if I do that, I keep setting my pointer down. This is also a bar magnet where this is the south pole and this is the north pole. And so this south pole is going to be attracted to that north pole and it's going to point like that. And so I would, by definition, describe the direction of the magnetic field there to be that direction. If I place that same compass right here, well, this south pole would be attracted to that north pole, this north pole would be attracted to that south pole, and it would point like that. And so I would say that the magnetic field at that location, would point this way. If I put that compass here, that north pole would be attracted to that south pole, and I'd get something like that. And if I kept doing this over and over again, I would get a whole bunch of vectors that would look like this. Now I'm going to pause here for the Canadian question of the day. Okay? If the north pole of a compass is attracted to a south pole of a magnet, why does it point towards Canada? Isn't Canada where we keep the North Pole? Isn't the North Pole where Santa Claus lives? The answer is Canada is where we keep the South Pole of the Earth's magnetic field. The Earth has a magnetic field that very, very closely simulates that of a bar magnet, where it essentially runs through the Earth, the bar magnet, where the South Pole here, South Magnetic Pole, is not that very far from the North Geographic Pole. And so what we find, if we remember the last slide, is that the magnetic field comes out of the north or out of Antarctica, where the penguins live, and comes back around into the south. And that's why here in Provo, those field lines are pointing quite a bit down of lower than horizontal, is because we're here where the magnetic field is coming down into the ground. Okay, see if your neighbor's on the bus. See if your neighbor's ever heard this before, this heresy. Now, now we complicate things with language, and we call this magnetic north because it's a magnetic pole, and we keep it in the north part of the in the northern hemisphere. We call it magnetic north, but indeed it is the south magnetic pole of the Earth's dipole. How's that for fun? Okay, I didn't come up with that. It was long before I was born. Long before I was born. And it turns out that this magnetic north, which is actually the location of the south pole of the magnet, wanders. Its cause is still something we're studying, but it's believed that it's due to the motion of molten metal, iron under the Earth's crust, and that's carrying some charge. Anyway, we'll talk about that more in detail later. But the wandering is pretty severe. For a while, it was just moving about 6 miles a year, and then it picked up recently and really started humming. Back when I was alive, it was down here in Canada, and now it's really up here headed towards Siberia, and it's not that far from the geographic North Pole these days. I have a friend that was on the faculty of Montana State, Lauren Acton, and he was actually a specialist on the space shuttle, and he studied earth science and physics, and he tells me that these poles can reverse themselves every 200,000 years. Evidently, that's what the geologic record is telling us. But we probably don't have to worry about that because the switching takes 2,000 years. Those of you that are, outdoors people, know that when you are trying to use a topographical map, you have to account for the fact that the magnetic north, which is really the south pole of the Earth, is not in the same location as the geographic north. And so on most of these maps, what they label as north is not the direction that your compass is going to point. Okay, and so you have to take that into account by knowing in the area where you're hiking what the declination is. If you are living in Chicago, if you look towards the North Pole where Santa Claus lives, you're also looking at the location of the magnetic north. And so they have it easy there. The declination is 0. Over here in Montana or Utah, it turns out that the magnetic north is a little bit to the east of geographic north. And this is an old visual. I checked yesterday, and here it's now only about 10 degrees east. Again, that's because of the wandering that has happened of the pole. Okay, magnetic field lines. You remember when we were talking about electric fields that they were messy. The electric field vectors were pointing every which direction. If we had glasses that could see those electric field vectors, we'd go stark raving mad. There's just too much information. And so we use field lines to paint a picture, to give us a way of representing the field everywhere in the room without so much clutter. And you remember the way we did that was we drew those lines so that they were close together where the field was strong. They were far apart where the field was weak. And the field, in that case, the electric field, was always tangent to those field lines. Well, we're going to play the same game here, where the direction of the magnetic field at any point is tangent to the magnetic field line at that point. So as an example, when we were looking at the magnetic field due to a bar magnet, we came up with a whole bunch of magnetic field vectors. But these vectors only tell me the direction of the magnetic field at a single point. Namely, this vector here tells me the direction of the magnetic field at that point at the tail of that vector. Now, the magnetic field lines due to a bar magnet would look like this. And you see, this gives me so much more information. Where these field lines are close together, I have a strong magnetic field. And your gut told you that. That's where the field is strongest, is near the poles. And out here, where the field lines are far apart, is a weak magnetic field. But everywhere the field line vectors are tangent to the field lines. The magnetic field vectors are tangent to the field lines. Now, I need you to appreciate something, okay? These iron filings help us visualize these magnetic field lines. And I searched the intertubes for days looking for a picture that would match up with these iron filings. And I think I did a really good job. Good job, Greg. Say it. Thank you. Little bit of feedback never hurts, okay? Yeah. Okay, now I showed you some pictures at the beginning of class of some solar prominences. And the way we understand those is that these are field lines coming out of a north pole and entering into a south pole that get loaded down with charged particles that are energetic, that are very, very high temperature. And then these, for reasons that we will understand in just a couple of days, these charged particles stream along these field lines. And when they get to the poles, they actually bounce and come back, and they go back and forth, back and forth. That was the purpose of that magnetic mirror machine that got scrapped at Lawrence Livermore National Laboratories, was to hold the charged particles in the bottle. Now, that's what we're talking about, okay? Those are very high energetic particles that are streaming along these field lines that make these big arches. Okay, now I have here a cathode ray tube, and it's a very, very simple device. Let me see if I can help you understand it. It's a vacuum tube. I get rid of the air inside, and there's just a cathode down here, which is just a metal disc, just something that I can hook my wire to. And then, down here, there's a, place to hit, connect the wire. And then it's got an anode down here. And so what I do is I make this cathode very, very, very negative relative to this anode, setting up a huge electric field, large enough to strip electrons off of this metal plate. And so electrons come racing, trying to get to this positive anode down here. Now, I'm going to turn off the lights. That doesn't mean you have to go to sleep, but it doesn't mean you can't. Now, oh, there's two projectors in this room. Who would have thought? That's more dark. Now you see that these electrons are stripped off of this cathode, and a lot of them go down the chute to the anode where they're feeling the draw. But some of them don't make the turn. Okay, kind of like a bullfighter saying, "Vole," okay? And so they just keep on going, and they go straight towards you. Okay, now I'm going to take a very strong North Pole and bring it up on the side of this, and we're going to predict what's going to happen there. Okay, so turn this back on. So, remembering that these are electrons, that dot represents the beam right here, coming straight towards you. And what I'm going to do is I'm going to bring in this North Pole right here on the side of the beam. And my first question is, what direction is the magnetic field at the location of the beam? Right here where the beam is, what direction would the magnetic field point due to this bar magnet? Tell your neighbor, what is it? What direction? Yeah, it comes out of the north and goes into the south. So it would point that way. Now, my bigger question is, what direction is, I'll tell you. This magnet's going to put a force on that beam that's going to cause that beam to deflect, to bend. And the question is, what direction is the force on the beam? This is our first clicker question of the day. Okay, now you can click. Remember, they're electrons. Okay, last call. Is that all of us? Whoa, okay. Looks like left one with right being a close second. Good job, people. Let's find out. I'm going to turn off the lights again. And Okay, the beam is coming towards you. And I bring the North Pole in. It went down. Did you see that over there in the cheap seats over there? It went down. Whoa. Whoa, only a few of you saw that coming. Okay, it went down. Whoa. Okay. I saw that coming. It goes down. Now, folks, that's gonna be a source of a little bit of struggle. The force we are gonna find is always going to be 90 degrees in direction from the field. There's always gonna be 90 degrees between these two vectors. And the bottom line is that magnetism is goofy, okay? And it's just a matter of time before Disney sues me for using that photo. Their lawyers will be breathing down my neck. So, what do we know about this magnetic force? Well, if we're looking for the magnetic force on a charged particle, it's important to notice, to know that the particle must be moving. If I had a whole pile of protons there, and I brought up a bar magnet, they wouldn't know. They wouldn't care, okay? They have to be moving. And it turns out they have to be moving a certain way. If I had a magnetic field in this room that was pointing towards a piano, I could fire charged particles, electrons or protons, in that direction or opposite that direction, and they wouldn't feel the magnetic field at all. They wouldn't experience a magnetic force, okay? They'd go along as if there was no magnetic field in the room. But if I tried to fire one of those protons or electrons across the field line, it feels a force. And because that force is perpendicular to well, that's the third part. The direction of that force is always going to be perpendicular to both the velocity vector and the magnetic field. Now, back in 105, we found that when something had a force and hence an acceleration 90 degrees to its velocity, what kind of motion did I get? Okay, circular. And so when these charged particles come streaming from the sun to kill us all, okay, they encounter the Earth's magnetic field, the Van Allen belt. Now, the part of the velocity that is along those field lines is unaffected. It just doesn't care. But the part of the velocity that's perpendicular to those field lines, it feels a force that causes it to go in a circle. So when these field lines come and hit the Earth's magnetic field, they spiral along the field lines. And those magnetic field lines we saw in an earlier slide come down into the North Pole, really the South Pole of the Earth, and come out of the South Pole, which is really the North Pole of the Earth. And so that's where you get these aurora borealis, and what do they call it down south? The Australian aurora, I don't know. Okay, I used to know. Now, how big is this force? Well, it turns out it's proportional to three things. It's proportional to how big that component of velocity is that's trying to go across the field. Is proportional to the charge on that particle, and also the size of the magnetic field. And so I can write it this way, where this is a constant of proportionality, okay? Is proportional to the charge, the perpendicular velocity, and the strength of the magnetic field, which we use a B to represent.
Why didn't we go up? And that would still be 90, and that would still be following it.
Ah. Very good question, and the topic of our very next slide, if you can wait for that one. Now, we've already defined force units as newtons, charge units as coulombs, and velocity as meters per second. If we choose the magnetic field units just right, we can make this constant go to 1 and simplify this equation. And that's what we've done, is we've defined the units of magnetic field to be the Tesla, okay? And that's to honor Nikola Tesla, not the car, okay? Now, it turns out that a Tesla is a fairly large unit. The magnetic field at the surface of the Earth is about 10 to the minus 4 Tesla. And indeed, that's such a more useful size that it's given a special name. 10 to the minus 4 Tesla we call a Gauss. And so the Earth's magnetic field here in Provo is about half a Gauss. Small bar magnet is going to be about 100 Gauss, or 10 to the minus 2 Tesla. When you go in and have an MRI, that magnetic field is a couple of Tesla. And people, when they tell you to take off all the metal jewelry and they ask you whether you have metal implants, tell the truth, okay? Tell the truth. I'll show you why in a minute. Now, all of these charges are going to feel exactly the same force because they have the same V perp. Okay, and you'll notice that the negative charge, it has to go the other direction to feel the same force. And what direction is that? That's the question that we have. Why do electrons go one way and positive charges go the other way? How do we find the direction? Well, we do it with a right-hand rule. You remember in 105, when we were talking about rotation, we had a couple of right-hand rules. And that's because when we were dealing with rotation, it was also goofy. You know, if I had a spinning wheel and I was trying to rotate it, it always went 90 degrees to the way I was trying to make it go. The torque was always 90 degrees from the force that I was exerting. And we needed a right-hand rule to find the direction of that torque. Now we've got the same situation here. If I have a charged particle that is traveling, there they are. If I have a charged particle that is traveling in this direction, in a magnetic field that is this direction. You know what? That red doesn't show up very well. Let's make that the magnetic field. We said earlier that this magnetic force has to be perpendicular to both of those vectors. So that means that if I can draw these vectors on a whiteboard or on a piece of paper, there's only two possible directions for that magnetic force. Either out of the board, which we would write this way, or into the board, which we would write that way. The magnetic force would either point out of the board or into the board. Well, how do I know which? I use the right-hand rule. There can't be a force unless there's a velocity. So the first thing you do is you reach in the direction of the velocity with your right hand. Now, this is the most important step. You have to turn your wrist so that you can wave your hand in the direction of the B field without breaking your wrist. Your right thumb is now pointing in the direction of the force on a positive charge. So this would be the direction on a positive test charge. And a negative would be pushed the other way. Okay? So let's go back here. I had negative electrons streaming this way, okay, towards you. And my magnetic field was pointing towards the piano. So if I turn my wrist so that I can wave in the direction of the magnetic field, that gives me a force up. And if these were protons, they would have deflected up. But they were electrons, so they went down. That make sense? Okay. Okay. So let's practice this. If I instead bring in my North Pole from up here at 2 o'clock, the direction of the magnetic field is always going to be away from the north. So that's easy. That's easy. So what about the direction of the deflection or the force on it? Well, again, I reach in the direction of the motion. That beam is coming towards you. And then I turn my wrist so that I can wave in the direction of the B field. And you see that my thumb is pointing this way. And then I remember these aren't protons, these are electrons. And so it's going to be deflected up that way. I'm sorry? No, the force is not coming towards us. The electrons are coming towards us. That's what this dot represents, is this beam of electron that leaves here and races out towards us. Okay? So the force is going to be that direction there. Do we want to see if we're right, or do we just believe that we're? Do you want to turn off the lights, or okay? Greg might be lying. He misled us before. Okay, so let's get this thing. Again, I'm going to come down at this direction. Okay. And did it happen? Yep, it came up the way we predicted. Okay. I love physics, it works. Man, it's different than biology. Okay. Oh, okie dokie. Now, let's do some clicker questions to make sure that we know how to use this right-hand rule. In this case, I have an electron and it's streaming to your right. And the magnetic field in the room, for some reason, points straight down towards the floor. And the question is, what direction would the magnetic force on that moving electron be? Let me get you started here. Okay, now you can click. Okay, last call, get your vote in. Okay. Oh, good, okay. I'm encouraged to see that most of you realize that there's only two possible answers up there. Because I can draw both the magnetic field and the velocity vector on this screen, and the force has to be perpendicular to both of those vectors, these two vectors define a plane, the plane of the screen. And the only directions that can be perpendicular to both of those vectors are out of the page or into the page. So to figure out which one it is, and it's out of the page, I reach in the direction of the motion, turn my wrist so that I can wave in the direction of the B field. That gives me into the page. Oh, but it's an electron, it's out of the page. Okay? Good. Now, I can rewrite this formula in terms of the total velocity by breaking up this velocity vector into two components. Normally I break up a vector into its x part and its y part, but it's more useful here to break up that vector into the part that is parallel to the magnetic field. That's this component here, and a part that's perpendicular to the magnetic field. Now you can see that this part that's perpendicular to the magnetic field is just that V perp is going to be the hypotenuse times the sine of this angle between the two vectors, right? This is the opposite side away from the angle, and the opposite side gets the sine. Okay, and so I can rewrite this formula for the magnetic force as the charge times the total velocity times the total B field times the sine of the angle between them. Okay, and we call that the Lorentz force, to honor again a dead physics professor, the Lorentz force. Okay, but what direction would this be? Well, it depends. Is it a positive charge or a negative charge? If it's a positive charge, it would be out of the board, out of the screen. If it were a negative charge, it would be into the screen. Okay, I hope everyone's comfortable with that right-hand rule. Now, there will be on the next exam a question like this. The Earth's magnetic field, as I said, is about half a Gauss, or 5 × 10⁻⁵ Tesla. And it points north and down 70 degrees, okay? Now, if I had a charged particle, an electron, that was moving due north, and when I say due north, I mean magnetic north, okay? We're not going to worry about the geographic north. If it's going due north, how big would the force be on that electron? Now, again, I just plug into this formula, the Lorentz force. I know what the Q is. The Q is the elementary charge. And you notice that I didn't put a minus sign there. I know that electrons are negative, but I'm looking for the magnitude of the force. I'm going to use my right-hand rule to get the direction of the force. Okay, I just want the magnitude. So there's my charge on an electron, absolute value. There's the speed at which it's going. Here's the Earth's magnetic field. And the challenge in these problems, and you're going to get one like this, is what angle do I use? Well, it's always this angle here. between the velocity vector and the magnetic field vector. And so if I put one arm in the direction of the velocity vector and one in the direction of the magnetic field vector, it's going to be this angle here, 70 degrees. And I plug into my calculator and I get a number that none of us care about. Now you might be saying to yourself, Greg, 10 to the minus 17 newtons, that's a pretty small force. Why do I worry? Well, that's because the mass of an electron is 10 to the minus 31 kilograms. And so the acceleration is going to be huge, enormous. If it were on you, it'd kill you dead. Okay, so it's a significant force on an electron, Now, in your homework, that charge isn't going to be pointing north, it's going to be pointing east. And so what you want to do is, take one hand and point it in the direction of the velocity east, and one in the direction of the magnetic field, which is north and down 70 degrees, and ask yourself, what's this angle between my hands right now? And that would be 90 degrees. If I told you that the particle was going straight up towards the ceiling, well, now what angle would be between the magnetic field and the velocity? Well, that's 90, that's 70, it'd be 160. So you have to, here's a little tip, a pro tip from an old man. When you get to that next exam, or when you're working on your homework, bring props, things that you can point, like different color pens, or those little, what do they call them? The pipe cleaners. Yeah, I didn't remember because I don't smoke a pipe. Pipe cleaners that you can bend, because these problems in magnetic fields are inherently three-dimensional, okay? Because that magnetic field force has to be perpendicular to these two vectors, every single problem is going to be three-dimensional. Some of us have no problem visualizing three-dimensional problems. Others of us are going to need the props, okay? You're going to need the props. Okay. What direction would this electron be pushed? Well, again, my right-hand rule says, reach in the direction of the velocity, swing your fingers in the direction of the magnetic field. That's going to give me a force on a proton into the page. And so this is an electron, so it would be out of the page. I hope that's getting boring. It should. This is why you don't lie about your implants when you go in for an MRI. This is a situation where there was a forklift in the room that someone neglected to notice, and then they turned on the MRI machine. You're going to be doctors, have mercy on this poor tech. Okay, they're feeling bad enough already. What would be the direction of the force on this proton if the magnetic field was up? Well, we reach in the direction of the motion. We turn our wrist so that we can wave in the direction of the B field, and that's going to give me a force out of the page. If I had an electron going the other way, I would reach in the direction of the velocity, swing my fingers in the direction of the B field. That gives me my right thumb pointing into the page, but it's an electron, so it would be out. The point I'm trying to make here is that I get the same force on a proton going to the right as I get onto an electron going to the left. And if I think of a wire carrying current as a bunch of positive charges going down a tube, I get a bunch of forces on that wire that are no different than if I think of the wire as having negative electrons going the other way. I get exactly the same force. And that's why it's okay to play the make-believe game that we've been playing with our circuits. And we just always call that conventional current. we pretend that the wire is a plastic tube with a bunch of positive charges going down the wire, okay? Now, really quick, another clicker question. The magnetic force on this wire is going to be right, left, into the page or out of the page. This current is conventional current, and it's going down, and that's the south pole of a bar magnet. In our department, that's a yellow end, okay? Okay. Oh, no, we haven't.
Oh.
Yeah, okay.
Well, actually.
Okay, last call. Should be another 3 of you, maybe not. Okay. Okay, we're still not sure, are we? Okay. Let's do this together. If I think of conventional current as the flow of positive charge, I reach in the direction of the motion or the flow, and I turn my wrist so that it's in the direction of the magnetic field. Well, the magnetic field comes out of a north, but it comes into a south. So that magnetic field would be pointing to the left. If I reach down in the direction of the flow, swing my fingers in the direction of the B field, I get a force that is into the page. So the answer was C. Yes.
How do you know if
How do I know what?
it's a positive or negative, they had learned.
Oh, we're always gonna, when we talk about current in this class, and indeed most of the universe uses this convention, we're always talking about conventional current or the flow of positive charge. We pretend that the wires are a plastic tube with positive charge flowing through it. Okay, that's gonna be our convention. Now, I have a fun demo for us that I call the jumping wire. I have a horseshoe magnet. Now you remember magnetic field comes out of a north, and this is my north pole here, and it goes into a south. And so the purpose of a horseshoe magnet is to create a magnetic field that's fairly uniform, that's not, you know, changing its magnitude drastically, like a bar magnet. And so I get field lines that are fairly evenly spaced between here. And if the north is on your left, those field lines would look like that, okay? Now I have a wire here, and when I turn on the power supply, it's going to take conventional current, the flow of positive charge, towards you. Now really quick, what direction will the magnetic force be on that? Yeah, otherwise we wouldn't call it a jumping wire, right? Okay, so the current's coming towards you. If I reach in the direction of the current and I swing my hand in the direction of the B field, I get a force that is up. Let's see if that's true. Whoa, that is so cool. We'll turn it off. Ow. Okay, now if I were to turn that around, what's going to happen? Yeah, it's going to try to go down. Okay. Now, I ask you, I ask you, what good is a jumping wire? I mean, have you found yourselves every now and again needing a jumping wire? Is that something that would be useful to you? And the answer is yes. Everything that you have in your life that has an electric motor in it runs on that principle of the jumping wire. All electric motors run on that principle right there. But more importantly, more critical to your personal happiness is that is the secret behind a stereo speaker in your stereo, okay? Now, yesterday, I spent a lot of my day creating for your enjoyment a stereo speaker, okay? I made it out of this Pepsi cup. And let me just, there we go. Another use of a Pepsi cup. Now, the way I made that is I just took a coil of wire round and around and around and around and around and around and around. Now, many of you have made electromagnets when you were younger, right? And the first thing you do is you take a nail and you make the wire go round and round and round and round and round and round and round. Okay, and that turns it into an electromagnet. Now, what I'm going to do is I'm going to pipe music from this. This is a CD player from the 70s. It was a difficult time. And that current's going to go around that coil. And then I also have a bulb in series with that coil so that you can see when there's music, okay? When there's current going through the coil, you're going to be able to see the bulb light up. So let me, it's going to take a moment to there we go. Now we got some music going. Okay. Now, I don't hear anything. Do you hear anything? Well, I don't hear anything because I'm deaf, but you should be hearing something. I'm going to take this fishing magnet, a strong neodymium magnet, and I'm going to put it near this coil. And so whenever there's current going through the coil, it's going to be attracted to the fishing magnet. Let's get a different song.
Albums, C minor chord, and inspirations as a songwriter. And I would love to kick things.
Can you hear music? Yeah. You know, at my age, that doesn't sound like music. I was hoping for something soft rock. Diana Ross is what I was hoping for. Now, I didn't say that was going to be a great speaker, okay? You're going to have to spend more money to get a great speaker. But that's the principle behind good speakers. Essentially, what we have is the same setup that I've got there. The back of the cup is acting as a diaphragm that's pushing air, that's compressing air, sending that signal to your eardrum that we talked about in 105. And in this particular setup, we have a circular permanent magnet where the north is in the middle and the south is on the outside. And so the field lines are these red arrows that go from the north to the south. When there's current going around this coil, that's going to give me a magnetic force out, essentially causing a compression that goes across the room to your eardrums, okay? Now, let's practice a little bit. I have this horseshoe magnet with a wire that's on a swing. And this is similar to what we're going to do in this week's or next week's tutorial. I'm going to send current. I'm going to first send it to your right. And this is the north down here, and this is the south here. You predict for me whether this is going to swing out or whether it's going to swing away from you in. Okay? So And it's conventional current that I'm gonna be sending to your right. Okay, how many say it's gonna swing out towards you? Away from you? Okay, let's find out. Whoa, yeah, out. Again, the flow was this way. The magnetic field goes
from the north on the bottom to the south on the top.
that's gonna be out. Now, if I switch those leads so that the conventional current's going the other way, it will go in. Okay? Good. Now, sources of magnetic field. Well, in 105, we learned something about Newton's third law. That if I push you, you push me. If something can exert an electric force on something else, that something else can exert an electric force back. Well, it turns out that if a moving charge gets pushed by a magnetic field, it makes sense that a moving charge should be able to create a magnetic field. And this is something that was discovered by Ørsted. And this is an inspiring story because it's one of the few times when something useful happened during a lecture, okay? Almost never does that happen. But Ørsted had maybe I'll just show the picture. There's Hans Christian Ørsted. He had a primitive battery that he was using to generate a current. And he just happened to have some lodestones nearby, some primitive compasses. And he found that when the current was going through the wire, he ended up with these compasses lining up in a circle. And that we can demonstrate. I'm going to make the current, in this, it goes up, so I'm gonna make the current go up through this wire. I'm gonna surround this wire with compasses. And let's see if this works. Yeah, it works. They line up. Okay. Okay. They are tangent to a circle like that. Now, what direction do those field lines travel? If I have current going up this wire, there's two ways for field lines to go around in a circle. And the way I remember which way they go is with my right hand. I have a straight part of my right hand, my thumb. I put that in the direction of the current, and the curved part of my right hand tells me which way those field lines wrap around. Now, we've run out of time, folks, but I've given you what you need to do your homework. Have a great weekend and good luck on that exam.